Dear students, in this video we will see an example for depth first search. When you apply this depth first search technique on this graph, what you finally get is a spanning tree. So our final output is a spanning tree. We also look for this DFS order, right? Now in this process, I am going to use a stack and one array called DFS array. Now let's start. From all these vertices, we have to choose one vertex as a starting vertex. You can choose any vertex. I am starting from A, mark it as visited by drawing some crossed lines like this, and immediately add that vertex to the stack and also add it to the DFS. Now the next step is finding out an adjacent vertex which is unvisited. Okay, so for this A, we have to find out an adjacent vertex which is unvisited. See here, we have this B as well as we have this D. Both of these vertices are unvisited. So you can choose either B or D. Any vertex you can choose. I am choosing vertex B. So you draw a red line from A to B and mark this B as visited and immediately add this B to the stack as well as to the DFS. And now consider the vertex B, and whatever you have done for vertex A, you do the same thing for vertex B. So what to do? You have to find out one vertex which is adjacent to B as well as which is unvisited. So first of all you write all the adjacent vertices. So B to A there is a edge, and B to D there is a edge, and B to C there is a edge, and also B to G and B to F also there is a edge. Among all these five edges, A is already visited, so just ignore this A, and all the remaining vertices are unvisited. So from these four vertices, you have to choose one vertex. Which vertex I have to choose? It is your choice. I am choosing the vertex D. So you draw a red line from vertex B to vertex D and mark this D as visited, and immediately add this onto the stack as well as add it to the DFS. And now do the same process for this vertex D. So first of all you just list out all the adjacent vertices which are not visited, right? So A is already visited, B is already visited, C is not visited. So write C, and E is also not visited. So there are two unvisited vertices for D. Among these two you have to choose one. Anyone you can choose. I am choosing the first one, that is a C. So you draw a line from D to C indicating that you have reached C from D, and immediately mark this vertex C as visited, add it to the stack and also add it to the DFS, and do the same step or same process for vertex C. List out all the adjacent and unvisited vertices. So E is unvisited and F is also unvisited. So among these two you can choose any one. So I am choosing this E. So you draw a red line from C to E, right, and mark this E as visited, and immediately add that E to the stack and add it to the DFS. And now consider vertex E. Now for this E, D is already visited, C is already visited, and G is not visited. So you reach this G from E and draw a line, and immediately you mark this G as visited, add it to the stack and also add it to the DFS. Now consider vertex G. See here, for this G, there are two adjacent vertices, that is E as well as B. Both of these vertices are already visited. Both these vertices are already visited. That means at this point you cannot move further. And whenever you reach a point from which there is no chance of moving forward, then you have to use a concept called backtracking. What is it? Backtracking. That means you have to perform the pop operation. That means G will be removed from the stack. And now what is on the top of the stack? Vertex E. That means you have to go back to vertex E. Okay. You have to go back to the vertex E and again do the same process. What is the process? Finding out the adjacent vertex which is unvisited. But if you observe, all the adjacent vertices of E are already visited. Like no, D is already visited, C is already visited, and G is also already visited. That means again you have to apply the backtracking. So you have to remove the top of the stack, that is E. Now C is present on the top of the stack. So again you have to go back to the vertex C. So come back to the vertex C and again apply the process. So if you observe carefully, for C there are 5 adjacent edges. Among these 5, already 4 are visited and F is not visited. So you have to draw a red line from C to F, indicating that you are reaching this F from C, right? And immediately mark F as visited, add it to the stack, add it to the stack, and also add it to the DFS. And now apply the same process for vertex F. So find out the adjacent and unvisited vertex. So unfortunately, all the adjacent vertices are already visited, like B is already visited, C is also already visited. So again apply the concept of backtracking, right? So come back to the vertex C, right? So when you apply backtracking, you have to perform the pop operation, and now C is on the top of the stack. So you have to come back to vertex C only, right? Now again apply the process for C. If you observe, all the adjacent vertices of C are already visited. So apply backtracking. Backtracking means remove the top of the stack. And now go to D. So I'm coming back to D, and all the adjacent vertices of D are already visited. So apply backtracking. So remove this D, and now on the top we have vertex B. So go back to vertex B and again apply the process. For this B also, all the adjacent vertices are already visited. So apply backtracking. That means B is removed from the stack. And next on the top we have A. So go back to A. And A is already explored. I mean, all the adjacent vertices are visited. So apply backtracking. So remove this A from the stack, right? And since stack become empty, right? So you have to stop the process, right? Remember, whenever a stack becomes empty, you have to stop your depth first search. And in order to get your final spanning tree, you have to remove the edges which are not red. That means which are not used in the process. Like no, see here from A to D, this edge was not at all used in the process. So you have to remove this edge. Remove this edge, as well as this edge also has to be removed. This one as well as this one. See here, after removing all those edges, finally this is your spanning tree. So in this spanning tree, there will be n vertices and n minus 1 edges. That means we have 7 vertices and 6 edges. And this is the algorithm for the DFS. Whatever the process we have done just now, so all that process can be understood from this algorithm. Just go through all these points, you will easily understand everything. Each and every step you will easily understand.